Hello everyone, we're going to continue today with 2.3. We're going to talk about the product and the quotient rules and higher order derivatives. The objectives that we'll discuss will be: find the derivative of a function using the product rule, find the derivative of a function using the quotient rule, find the derivative of trigonometric functions, and find a higher order derivative of a function. So we'll begin by talking about the product rule. The product rule is used whenever you are taking the derivative of a product of two functions, such as in this theorem. It specifies that if you have two functions being multiplied and you're taking the derivative of them, then the process of, or the technique to find the derivative will be by using a sum of products described in this form. In this case, we have the original function, the first function multiplied by the derivative of the second function, followed by a plus, and then now the original second function multiplied by the derivative of the first function. Or also, we can also think about it in this way, right? We can say that this is the same thing as having the derivative of the first function multiplied by the original second function, plus the second function multiplied by the derivative of the second function. In either case, the way you guys want to remember, you have to memorize exactly this, but what I'm trying to say here is, if you guys notice, this seems like you're doing two products, right? You're adding two products, and it seems like you alternate which one you will take the derivative. Either you take the derivative of the second one and multiply by the original of the first, and then you add it to the derivative of the first one multiplied by the original second one, right? So it doesn't really matter the order. As long as you do that alternate, then you will be fine. You will see here that I often refer this to be u times v. So I sort of write this when I'm doing the problem to kind of guide you guys. But what I'm trying to say here is that you have the u represents the first function, and then the v represents the second function. So I'm sort of mimicking the same theorem, and I'm saying u prime times v plus u times v prime, right? So I'm sort of mimicking the same process, but with other letters, so that it's easier for us to follow through, and I'm not becoming too specific here. This rule can be extended to the product of three functions, and it becomes three terms in that way. So let me just jump in first to an example. You guys can see how this can be done. Now, there are some functions that you don't have to do the product rule, but sometimes it's actually more practical to do the product rule, right? So in this example, I could have easily just simplified the expression. I could simplify the expression first before applying the derivative, right? I could have simplified that by distributing the whole thing. And then by then, I could have used a combination of the power rule along with the sum and difference rule that we talked about yesterday. But the point here is that obviously I'm going to give you guys an easy problem first to sort of explore this rule. But there's a lot of problems where you can't go around it, and you have to actually apply the product rule. So bear with me that yes, although there might be an easier way to do this, for now, we're just trying to practice the process of using the product rule. And then I'll point out some of the common mistakes the students will do, and so hopefully for you guys to make a note and you guys don't make that silly mistake. So here we go. We'll begin by finding the derivative of this, right? So I'm going to apply the rule. So here, if you guys notice, I have the u times v prime, and then I'm going to follow this process. Now, my recommendation for you guys, and you guys will find it silly right now, but believe me, this will help you at the end of the day. If you guys notice, what I did here is I sort of kind of went and kind of set up the derivative. If you notice, I said, okay, the derivative of h will be the derivative of the product of this. So I went out of my way, I put the product inside this bracket, so I added these brackets, and I put this mark right here saying that I'm taking the derivative of this product, right? So I haven't done anything, right? It was just sort of kind of like a setup, sort of giving me an idea what am I doing. So that sort of gives me a context that, u represents my first function, and then v represents my second function, right there. So you guys will see here that I'm taking u, the derivative of u, and that's right there, derivative of u. Now I put this, I didn't take the derivative, I sort of also set it up that way you guys can kind of follow through. And then times v is this is the original v, right? It doesn't have a prime, so I'm just gonna leave it in the original form, and then followed by the plus, and then followed by again the original function u, and then followed by the derivative of v. So you guys see here the derivative, and I put this prime there to tell me that I'm taking the derivative of that. So you see that that's a nice setup for us to be able to follow. Now all I have to do, I don't have to worry about the formula anymore. All I have to do is do as I am being told in this last line. So in the first line it says take the derivative of the yellow, right? So what is the derivative of this? Well, what rule I'm going to use? I'm going to use the constant function, the power rule, the difference, all those combinations of rules. So I'm going to say, okay, the derivative of 3x, well, the derivative of 3x, the 3 will carry, and I'm going to multiply by derivative of x. Remember, the derivative of x is 1, so that's 3 times 1, followed by the minus, followed by the derivative of 2x squared. Well, the 2 will be carried over, and then I'm going to multiply by using the power rule. I'm going to multiply by the power, right? So it'll be 2 times that 2 multiplied by x, and then subtract 1. So I have 2 times 2 times x raised to the power of 1. So 2 times 2 is 4 times x raised to the power of 1. So I did that in my head, right? And I hope that you guys by this, when you guys are doing this, you have already some practice there. And I'm just gonna copy and paste the second one, right? I don't have to do anything because that's not a prime, right? That's not a prime. Followed by the plus, followed by the yellow one, which doesn't have a prime, so I'm just gonna leave it as it is. And then followed by 5 plus 4x prime, which means I'm gonna take the derivative of this. The derivative of a constant is 0, plus the derivative of 4x. What happens to the 4? It carries over. Multiplied by the derivative of x. I remind you guys the derivative of x is 1. So I technically multiplying 4 times 1 here. So that's a 4. And that's it. That is the derivative right here. That's technically the derivative. And for the most part, I'm okay with this a lot of times. But a lot of times what we're going to be doing in the future, and there's a whole chapter of this, where we're going to focus on one of the steps that will be essential, and it will be to factor this out. So we're going to practice here for now, just sort of simplifying this whole thing, which means, remember your algebra, when you multiply two binomials, you distribute, and then you get 3 times 5 is 15, 3 times 4x is 12x, minus 4x times 5, negative 20x, negative 4x times 4x is negative 16x squared, followed by 4 times 3x is 12x, followed by 4 times negative 2x squared is negative 8x squared. And then combine like terms, I see the negative 16x squared minus 8x squared gives us negative 24x squared. 12x minus 20x plus 12x gives you 4x, and then followed by 15. And there you go, right? So, but I remind you guys that this setup was sort of important, and I encourage you guys to sort of adopt this technique, right? I encourage you guys to practice the following here. In fact, let's see. Maybe I'll do actually one of these. I'll do this one, the first one here. So if you don't mind me here, I'm going to use this space. So I'm going to have y equals 3x squared sine x. Now, first thing you have to identify is the fact that this is a product of two functions. Now, does it help if I actually come back and I sort of label what are the two functions? Yeah. It might be clear for you guys. Remember that sine of x is its own function. So there you go. And then this over here is its own function. So I can make it more clear for you guys. I don't have to, but it kind of, and for now I will do that for you guys to make it clear that that's why we're doing product rule. So I'm going to take the derivative of this product, right? So I'm going to put that as a prime, right? that means that I've already taken the derivative in my mind, right? And sort of, so now I'm going to follow the rule that says take the derivative of the first one. So that's my derivative of the first one, multiply by the second one. There you go. Followed by the plus, followed by the first one, original, multiplied by the derivative of the second one. And there you go, right? That's why I put the prime there for that one. All right, so now that's it, right? That's the derivative in my mind. That's set up. But now let's come back and apply the derivative to each of the factors. Now, you guys notice that by doing this, I don't have to think about the product rule anymore. All I have to do is focus on doing this derivative. To do that derivative, I go back to the power rule. So I have the 3 that carries over, and then the power rule for x squared is going to be 2x, right? Followed by the derivative, followed by just sine of x. No need to write the derivative there. Followed by 3x squared, and then the derivative of sine is cosine of x, right? So there you go, I did this, right? So everything is product, 3 times 2x times sine of x. So I'm going to go ahead and multiply that as 6x sine x, followed by 3x squared cosine of x. Now this is technically the answer, right? This is just this is now the derivative of y, but I could factor an x if I or a 3 if I want to here, and I'll do that just for an alternative, just for us to get used to factoring here. So we're gonna get 2x sine of x plus x cosine of x, right? And so there you go, right? So I'm gonna write this as y prime, right? That's y prime, not y anymore, but this is y prime. All right, so I want you guys to try the other one, and then so that was it, right? That's the product rule. We'll do more practice in class, but if you guys want to try a few more, you guys can try the practice number 3. So the next one, the next rule that we're gonna talk about is the quotient rule. The quotient rule happens to be the rule that you will use to find the derivative of a quotient. In other words, find the derivative of a function that looks like a division, right? That looks like a division. So let's follow the rule here that we have, right? We're assuming that f and g are both functions that are differentiable, where g of x is not equal to 0. That's just to cover our requirements. Now what's happening here, let me describe what's happening. So you have two functions, the numerator and the denominator. So the derivative of this quotient happens to be this this formula. That means you take the bottom one, the bottom function, and then you multiply it by the derivative of the top function, followed by a minus multiplied by the top function, minus the top function times the derivative of the bottom function, and then divide the entire subtraction by the bottom function squared, where g of x is not equal to 0. Now you guys will hear me saying this in the recording, and also tomorrow in the lecture on Thursday. But I often refer this to what we call sort of follow this jingle that I learned when I was when my teacher used to do this process. So my teacher used to separate this into a high function and low function. And if you're taking the derivative of this division, then my teacher used to do this. It used to say, start with a low, right? Low d high minus high d low, square the bottom, and there you go. So if you guys want to, I will say this again a few times so you guys can kind of practice with me. So low d high minus high d low, square the bottom, and there you go. Low d high minus high d low, square the bottom, and there you go. So this will help you remember the formula. Now remember, you gotta start with low, and you notice that what this means is you have low multiplied by the derivative, d for derivative of the high, minus the high times the derivative of low, d for low, right? Anyway, so you'll hear me that, and that's a lot of times what I actually do in my head. All right, so we have this division, right, of two functions, 5x minus 2 all over x squared plus 1. So we clearly have to use the division. We have to use the quotient rule. And so we're going to follow that strategy, right? So I have low d high minus high d low, square the bottom. There you go. So I'm going to set it up. I'm going to say, okay, I already have y prime, right? The derivative of y is y prime equals the derivative of this. Well, I put some brackets here and I put a prime to tell the reader that this is the derivative, right? And now I'm going to go ahead and execute it. So I have low d high minus high d low, square the entire bottom, and there you go, right? Now that I've done the formula, now I don't have to worry about the formula anymore. I just have to apply the derivatives that I have in front of me, which are these two. So x squared plus 1 is x squared plus 1. The derivative of 5x minus 2, the derivative of this, I'm going to have to use power rule, right? The derivative of 5x is follow the 5 and then carry the 5, and then the derivative of x is 1, so that'll be 5 times 1, minus the derivative of a constant, which is 0, right? Like the derivative of a constant is 0, so that's just going to be 5. And there you go, right? I already found the derivative of this. Minus 5x minus 2 times the derivative of x squared plus 1. The derivative of x squared plus 1, what's the derivative? Well, you do one term at a time. The derivative of x squared, remember that you copy and paste the power, multiply by x, and then take away 1 from the power, right? So 2 minus 1 is 1. The derivative of a constant is 0, so that goes away, so we only have the 2x. So you notice that there's no more primes. I've executed all of them. So now I'm going to go ahead and simplify this. So obviously I'm just going to follow the distribution. I just follow whatever the math that I have here. Now in the second part, I'm going to be careful because there's a minus in front of it, so I'm going to sort of distribute negative 2x. So the first part is easy. 5x squared plus 5. The second one will be negative 2x times 5x gives me negative 10x squared. Negative 2x times negative 2 is positive 4x. Because negative times negative is positive. All over x squared plus 1 squared. Now do not expand this. Please do not expand this. It is assumed, and we usually never actually expand this. Actually, it's better actually to leave it like that. And then we'll simplify this by combining like terms. 5x squared minus 10x squared gives us negative 5x squared, followed by the 4x, followed by a 5. And there you go. That's pretty much it. So we found the derivative using the quotient rule. There's a few more examples here that we can use. So here's another example. I'll do this on the side, so for us to have a little more practice. All right, so I'm gonna write the function, and I'm gonna write 1 over x as x to the negative 1, just to make this simpler. Now in this case, they're asking us to find the equation of the tangent line to the graph. So actually we're not looking for this, we're actually looking for this, right? So we're looking for the equation of the tangent line. So we need to find m and we need to find b. Now how does m relate to this function? Well, the equation of the tangent line at f of x at that negative 1 point, they're going to both have the same slope. So if I can find the slope of this, then I can find the slope of this. That's how these relate, right? So I'm going to go ahead and do that. I'm going to find the derivative. The derivative of this is going to be, I'm going to go ahead and set it up. So it'll be low d high. Oops, I don't think this is gonna fit. Let me do this here on the bottom. Okay. Low d high. Sorry, I almost forgot my prime. Low d high minus high d low. So derivative low. Square the bottom, there you go. Alright, so the derivative continues. This x plus 5 will stay the same. the derivative of this product is going to be bring down the power, so that'll be negative, so it'll be positive 1, x, and then negative, and then take away 1 from the power, so that'll be negative 2, minus 3 minus x negative 1. The derivative of x plus 1 is going to be 1. And then technically this is the derivative, so I don't have to do too much of the algebra in this example, because I can just go ahead and apply. I know that we're looking for the derivative of this, so m will be whatever the derivative is for x equals negative 1. So I'm just going to go ahead and place in there negative 1 plus 5, negative 1 to the negative 2, minus, maybe I'll do that on the bottom part as well, that 1 just goes away. Okay, so if I compute that, then I get the slope, and I'm running out of space here. So let me do this in my head. So negative 1, move to the bottom part, that's going to be a square, that's going to be a 5, and then that's going to be a 4. So that's going to be a 4, followed by 1, 3 minus 1 is 2, so that'll be negative 2. Negative 1, 4 square is 16, so you have 2 over 16, which is 1 over 8. So that's your slope. And then we're going to continue with this by finding the rest of the equation. So now we need to find what's b. Now we know what x and y are. That's going to be, we're going to replace those in here, so that's a 1, and that's 1/8 of negative 1 plus b. By using this equation, because this point is both in the original function, but it's also in the tangent function, the equation of the tangent, they both have the point is a solution of the equation. So this is going to become negative 1/8. And then if you add it on both sides of the equation, you have 8 over 8 plus 1/8 equals b, so that gives you 9 over 8. So technically here we have the y equals 1/8 x plus 9/8. That's the equation of the tangent line. But what I was trying to focus here was the quotient rule. We've done this problem a few times, but want to make sure that we still know how to find the equation of the tangent line. But mainly in this example, we were focusing on using the quotient rule to find the derivative. A few things I want to mention, and obviously you can pause the video anytime you want, but if you guys want to catch up or take a break. Now, what I'm going to talk about here is that even though some equations or functions look like a quotient, it doesn't mean you have to do the quotient rule. Let me say that again. You don't have to do the quotient rule all the time. For example, here, and the clue is this: if you have a quotient, whenever one of the and your denominator is a constant, you notice that's a constant, you don't have to use the quotient rule. You could, and it will work and will give you the same answer, but you're gonna work twice as hard, or maybe 3 times as hard. So in this example, because it is a constant, you can just carry it outside. You can just do this, right? You can just do 1/6 times x squared plus 3x, and then you can do the derivative of that. Same thing here, then this will be the same thing as this. Or you can just leave it there and just apply the derivative of the top. So so what about this one? Well, even this ones you don't have to. Let me explain why. Because you have a constant there, right? So you have a constant there, so you can just move this to the top by changing the sign of the power, right? Sign of the power, and then you can just apply the power rule. So you don't have to do this again, the quotient rule. What about this one? It seems like we do have a function because there's an x there, and you have x's on top. Even this one, you don't have to. What you could do here instead is to simplify, distribute this, distribute that, and then simplify the equation like that, right? Divide every term by 7x, and then this will give you an opportunity for you to use power rule again. So we do say, we recommend that if you don't need to use the quotient rule, then there's something, I always apply the rule that's the most practical and easiest way. Now, is it wrong to use the quotient rule when you can use the power rule? No, it's not wrong. And if that's the only way you thought about doing it, then that's fine. Unless if I specify, hey, do this problem using the quotient rule, do this problem using the product rule, or I ask, please simplify the expression before you apply the quotient rule, something like that, then follow directions, obviously, right? Always. All right, moving on to the next functions. We're going to talk about the trigonometric functions. We already talked about sine and cosine, right? The derivative of sine is cosine, and the derivative of cosine is negative sine. Now there is a few more that we need to discuss, and that is the tangent and secant, cotangent, cosecant. Now here's a rule of thumb. Just remember this. TSS, and then TCC. Okay, remember this. So what I'm saying here is, if you're taking the derivative of, let me use a different color here. If you're taking the derivative of t, notice that the derivative of t will be secant, right? Secant times secant, so secant square. Do you guys see that? The derivative of tangent is secant square. So in other words, secant times secant. Now this also works backwards. If you notice, if you take the derivative of secant, sorry, I erased the other one. If you apply the derivative of secant, then the derivative of secant, what's left behind? A tangent and a secant. So secant tangent. Do you guys see that? So just remember these two will help you remember the derivatives of each one. TSS, right? Same thing with over here. Now in this case, instead of because they're all going to be CC's, I'm going to let cotangent be the T, right? So if you have the derivative of cotangent will be CC, meaning cosecant times cosecant with a minus in front of it. So the derivative of cotangent is negative cosecant square. And if you do this backwards as well, it works the same way. If you think about it, if you find the derivative of cosecant, the derivative of cosecant will be negative tangent cosecant, negative cotangent, negative cosecant. Sorry about that. I almost was thinking about something else right now. So negative cosecant cotangent. So just remember that combination, and that will be very helpful to remember these derivatives. In fact, my wife kind of showed me this little pattern. Otherwise, I used to memorize all these ones. Anyways, so let's apply a few of these derivatives. So here we have the derivative of y equals, if we're given a function y equals x minus tangent x, we find the derivative of it. We're going to do this one piece at a time, right? The derivative of x, we know it's 1. Followed by the minus, followed by the derivative of tangent. We know the derivative of tangent is secant times secant. So secant square of x. That's it, right? What about this one? Well, in this case, you have a product of two functions, right? You have x multiplied by the function c of x. So clearly here we have to use the product rule. So I set it up, right? We have the derivative of the first one multiplied by the original second one plus the original first one multiplied by the derivative of the second one. By applying the formula, now I can just focus on doing one piece at a time. The derivative of x is 1 times secant of x plus x times the derivative of secant is secant times tangent, right? And then you can notice that they both have a secant in common, so you can factor the secant. So factor the secant from both terms, and you're left with 1 for the first term. You're left with the x and a tangent for the second term, right? All right, so here are a few more examples for you guys to follow and simplify after you differentiate, right? We tried to simplify these. Now remember that the easiest part is the calculus part. The most things that people will have trouble with is with the algebra. Moving on to the next part, we're gonna talk about the connection between position, velocity, and acceleration. We talked about the relation between position and velocity last time. We actually said that the derivative of a position function is velocity, and that is because we know that the derivative of position is the rate of change of a position, where the rate of change of a position is the description of velocity. So, but moreover, we have that we got that the derivative of velocity, if you take the derivative of velocity, that actually gives you the acceleration, right? So that's kind of neat, right? So if you guys think about this, we have the first derivative of the position gives you velocity, but if you take the second derivative, meaning the derivative of the derivative, it gives you the acceleration, which actually introduces this concept that we can take the derivative of a derivative. And why not? Since we know that we're taking the derivative of a function, and the end result is another function that is also differentiable, right? Then you can continue taking the derivative of that and continue to do that, because that's actually, even in math, in the real life we have a connection to the real life. We just learned that the second derivative of position happens to be the acceleration. So that's sort of interesting. It's mind-blowing. So let me just read a few things here. The function a of t is the second derivative of s of t and is denoted by the second derivative of t. So we notice here we have a double prime, right? So we call this s double prime. The second derivative is an example of higher order derivatives. You can define derivatives of any positive integer order. For instance, the third derivative is the derivative of the second derivative. Higher order derivatives are denoted as follows. So here is the first derivative, y prime, f prime of x, dy dx, derivative of f of x, and this, and so on, right? The second derivative is y double prime, f double prime of x, the second derivative of y in respect to x, and so on and so on. Third derivative is y triple prime, f triple prime of x, derivative of y, the third derivative of y in respect to x. And you guys notice that once you pass the third derivative, we don't do any more of those tallies, any more of these primes, right? We actually just write the number, but we put parentheses so that we don't get them confused with powers. So be careful, because this means something different, right? Versus this. So this means that this is a derivative. This means that this is a power. So be careful. Now, and you guys will see it's more clear when you use it with the function. And that means you're just taking the derivative of the third derivative, right? And so on. So there's no limit here. You can actually go and take the derivative and continue to do the derivatives for some functions, specifically for those periodic functions. But also there's a lot of functions that can have many derivatives. So infinite derivatives. So let's find the acceleration due to gravity. So because the moon has no atmosphere, a falling object on the moon encounters no air resistance. In 1971, astronaut David Scott demonstrated that a feather and a hammer fall at the same rate on the moon. The position function for each of these falling objects is given by the position function s of t equals to negative 0.81 t squared plus 2, where s of t is the height in meters and t is the time in seconds. The question is, what is the ratio of Earth's gravitational force to the moon's gravitational force? So what we're gonna do here, since we're given the position function for the moon, why don't we find the acceleration, which happens to be the gravity, so of the position. So take the derivative of the derivative, and that will give us acceleration, which acceleration is, in this case, represents the gravity of the moon. And that's what we did, right? So we have the position function, and then we took the derivative. That means that's the velocity. The derivative of this means, what do? We take the constant, carry over, multiply by the power by 2, multiply by t, subtract 1, and then add the derivative of constant. The derivative of constant is 0, so that means it goes away. So if you multiply these two together, that gives you negative 1.62 times t, and that's your velocity. But we're looking for the gravitational force, which is denoted with the acceleration. So acceleration and gravity, right? So gravity is an acceleration factor. So take the derivative of velocity, and that will give you acceleration, which means the second derivative of the position. So the derivative of the derivative, so we take the derivative of this, is negative 1.62 times t. Well, the constant carries over, and then you ask yourself, what's the derivative of t? It's going to be 1. So we find out that the gravitational force on the moon is negative 1.62 meters per second. Now we're talking about seconds, so therefore we're going to compare this to the gravitational force on Earth in terms of meters, right? Sorry, and I meant that we're doing meters here, so that's why we're going to deal with meters here. So the ratio of the gravitational force on Earth is the gravity factor, which is negative 9.8 meters per second. And then we're going to divide this by negative 1.62. Hence, we get the ratio 6.04. So the ratio between the Earth gravitational force and the moon's is the ratio is 6.04. So we can see that the gravitational force on Earth is greater 6 times than the moon's, right? Now we want to make sure that we understand why we did Earth versus over moon, and that's because they specified it over here on the question. What is the Earth gravitational force to the moon's? So the order that comes in the sentence, that's the order we're going to do the division. Now if this was backwards and they said, what is the ratio of the moon's gravitational force to the Earth gravitational force, then these two numbers would have been flipped. It would have been negative 1.62 all over negative 9.8. So the order for which appears in the sentence matters in mathematics. All right, so that's pretty much it for this for today. So we discussed the product rule, the quotient rule, and the higher order derivatives. We also connected the last piece of connection between position function, velocity, and acceleration. But moreover, I want you guys to really focus on mastering the quotient rule and the product rule. We'll have a few examples in class to practice. But as I mentioned before, focus on the setup. If you set it up correctly, you're almost guaranteed to get it right. All right. So I hope this is helpful. If you guys need to watch it again, please do so. Remember that there is always a gear there. You can fast forward or slow down. Have a great day, and I'll see you guys in class.